All right, in this lesson, we're going to be taking a look at section 3.6, the method of undetermined coefficients. Before we get started, let's just review what we've been thinking about recently in some of the previous sections. Take a minute to do this warm-up, and we'll check our answers in just a second. Okay, hopefully you paused the video and you had a chance to take a look at this. Hopefully this is a pretty quick and straightforward warm-up. You're gonna try as your solution a solution of the form e to the RT. You're gonna get this for your characteristic equation. Factoring and solving gives these as the roots, and of course this is like the general solution. So the set of two solutions that we're thinking about right now are e to the 4t and e to the negative t, and we're asking then, do those, just let's verify that those do in fact form a fundamental set. So checking the Wronskian gives negative 5 e to the 3t, which is, it says equals 0. Should say not 0. Here, I'll fix it right now. It should say not 0, which is not equal to 0. So therefore, this is in fact a set of solutions. It's a fundamental set. It's linearly independent. We can use all of those words. So today we're going to take a look at the method of undetermined coefficients, and for the first time we're going to be able to solve a non-homogeneous equation. That is something that has something other than 0 on the right side, a second order linear differential equation that has something other than a 0 on the right side. That's the goal of today's lesson, is to solve some of these kinds of equations that look like this. See the g of x on the right side? That's called the non-homogeneous part of this equation. And what we'll see here today is that every solution to such equations is a combination of the homogeneous component. We'll call that solution, which we have also been calling the general solution to the homogeneous. That's like the part we've already been doing, right? And then there's going to be some other particular solution called yp, we'll call it, and we'll combine these. Obviously, if yh will work in the differential equation plus yp, because you can see if you plug that into the differential equation, you'll get yh will give 0 on the left side, and yp will end up giving the g of x. So when we combine those, it'll work. So you can check it out. See, look, when you plug these in, you'll get, notice, the green stuff gives 0, and the red stuff gives g of x. So that works. So you can see just even here with the mathematics that's been shared on this slide, you can see that there's like kind of a way forward here. The way forward is going to be to find, in all of these kinds of situations, to find the homogeneous solution, which we've spent some time thinking about in the previous sections. That is, solve the equation as if there is a 0 there. And then we're going to need to find a particular solution, and then we're just going to need to combine those. So that's the kind of the way forward today. How do you find the particular solution, though? That is an interesting question. So the method, there are two methods we're going to share in this unit. The first method we're going to talk about is the method of undetermined coefficients. It's a really good name for what you're about to experience here. So let's say the non-homogeneous function, the g of x term on the right side, is some kind of standard function of the forms that are written here. Now there could be other functions like logarithmic functions or other trig functions such as tangent, which would be not so convenient. The functions we're looking for here are functions that have derivatives that can be written in terms of finitely many functions. Like, for example, if you use tangent, the moment you take the derivative of tangent, you're going to get secant squared, and then you're going to get 2 secant secant tangent, and then you're going to have, after that, like a whole bunch of product rules to negotiate. And as the derivatives go on, you're going to get like more and more complicated combinations of things. And so it's a little trickier to see how that would work. So the examples of these functions we're looking for are functions typically are going to have polynomial, exponential, or sines and cosines. And any combination of those will be fine too, like sums or products of those functions are all going to be ones that we can handle. Some of them are going to be a little intense, like that last one. I wouldn't necessarily want to do that one, but it's doable by this method. All of these would be. So we'll see more what we mean in just a second. So we're going to refer throughout this lesson, and we're going to do like a day 2 on this topic as well. We're going to always call this the UC set, the undetermined coefficients set of a function. The set of functions that all the function itself, together with linear independent, together with all the derivatives of f, any constant multiples or linear combinations of those. So just as some examples here, I've stolen this from somewhere. You can see, for example, if you have, let's look at a few of these and maybe mention. I won't talk about every single one. You can take a look at them. But like, so for example, if you have something polynomial, like let's say you have a cubic, then you know that its derivatives will all be itself, and all of its derivatives will be of the form something that's polynomial, right? So there's no derivative, the function, the first, the second, and the third derivative, all of those will be accounted for in this kind of an expression with the correct choices of A, B, C, and E. How about D? I don't know. Okay, what about the sine and cosine ones? Like, let's look at sine 4x. Now, if you take the first and the second and the third and so on derivatives, you're always going to get things again of this that are going to be in this set of functions of this look, right, where A and B are chosen correctly, right? But even we won't need it in this context, but let's say you want the 10th derivative of this. Well, it's going to be this with the correct choice of A and B, right? And the same thing would go for, honestly, if you did sine of 4x plus cosine of 4x, you're actually going to have the same form here, right? You're going to get like linear combinations of these things. I think it goes without saying that all the derivatives of e to the 5x are going to be something times e to the 5x. But then we can kind of do these combinations of things. Like, for example, in number 9 here, x squared e to the 5x, that's going to have, think about its derivatives. It's going to be, you're going to need to use the product rule. So it gets a little messy, but still all the every term of the derivative will be of the form something times x squared e to the 5x, or something times x e to the 5x, or something, just a constant, times e to the 5x. So that's captured here. It's kind of been in it's appearing here in its like factored form. But I think you get what I mean. And then the same thing goes, take a look, just to take a moment and pause this and take a look at the other ones and kind of verify that, yeah, if I were to take any derivative of any order of this expression here, or here, 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 that I'll get something that's kind of accounted for in the expression on the right. So take a second just to study some of the things on that list. That forms kind of the underlying motivation for how we're going to move forward with this. We're going to kind of assume a particular solution with unknown coefficients and section 3.6, the method of undetermined coefficients, and then we're going to try and figure out what they are. So let's try one of these together. Here you can see on the left side, that doesn't look too intimidating, but what are we going to do with this 3 e to the 2x? Well, the way we're going to handle that is first, we can proceed as if it's 0 on the right side, just solve the homogeneous equation. Thankfully, we already did that in the warm-up today, so we'll just write that down again, but hopefully that's kind of become second nature to you. Now, is this one of our UC functions, the red function on the right, the non-homogeneous term? And the answer is yes. This is a pretty safe one. It's like, of course, it's going to be this e to the 2x, and so the form of the solution will be like some constant times e to the 2x. And we'll now take derivatives. We just need the first and the second derivative. And now we plug those in to our equation in the spots where it goes. There they go. And you can already maybe kind of see where this is going. We're going to collect terms and solve for, here it's not too bad because there's only one unknown coefficient. And so as we collect like terms, the coefficient on the left side just needs to be the same as the coefficient on the right side, which is 3. And that will admit the value of A. So let's take a look at what, you feel free to pause and solve that for yourself. See if you can figure out what A is before I tell you. right, so multiplying things out, collecting like terms. Did you get a equals negative 1/2? Good. So now let's see if we can figure out. We got to zoom back out. What have we done? Okay. Well, we said originally, I think we well justified this, that whatever the solution to our equation is going to be a combination of YH and YP, the solution to the homogeneous equation, the green thing, and the particular solution that we have just found. So there it is in green and red in all of its glory. And I think it's pretty clear to see. You can double check it if you like again in the equation, but that is the general solution to that equation. Feel free to plug it in and try it. Obviously, this can also be done in the context of an initial value problem as well. And then you'll need to resolve the constants C1 and C2. All right, let's try another one. This time we've got the same, just for the sake of this lesson here, we've got the same equation on the left side. We've already solved that one. This time the UC set, the undetermined coefficient set for that function sine x on the right side is going to be sine and cosine. So can you already say what you think the form of our particular solution is going to be? Think about that chart. I gave you some of those sample ideas. Think about the derivatives of sine and cosine. Yeah, it's just going to be that linear combination of a sine x plus b cosine x. Taking the first and the second derivative gives those things here. And, well, I think maybe you get the way forward on this. Go ahead and, whenever you like here, pause the video, but try and beat me to the punch. Plug y double prime, y prime, and y in to where they go. This is in the original differential equation. Notice what I've done on the right side. Also, I've expressed this as 2 sine x plus 0 cosine x, just to emphasize what the coefficients are going to need to come out to be. And now I'm collecting terms that have a sine and terms that have a cosine on the left side. And I've color-coded these. The blue needs to equal 2, and the purple needs to equal 0. And so what that gives us is a little system of equations. We're going to have negative 5a plus 3b equals 2. There's your first equation. And negative 5b minus 3a equals 0. There's your second equation. Again, I encourage you to hit pause and try solving that before I do. You can use any number of different system solving methods that you like. Okay, so if you've done it, over here I'm going to choose substitution as my method. I solved for b in the second equation, and now I'm substituting that into the first equation, messing with a few fractions there to get, it's not really a great number, but there we have it. And b is also a wonderful fraction as well. Okay, so we don't mind fractions. Now we can combine our solutions, our homogeneous solution, which is the same as before, together with now the particular solution with the constants that we found. Okay, let's try a polynomial one. Again, we're really creative on the left side. Same homogeneous part on the left side and the same solution. So what about x squared? Well, here we've got the undetermined coefficient set. Think about the derivatives of x function and its derivatives, x squared, x, and 1. So a, b, and c. Now we've got 3 constants. Oh, okay, very exciting. Take the first and take the second derivative. Substitute, and again, please don't let me stop you. Hit pause and try this, but you see if you can land this yourself before I do. Substitute those in. Notice the use of kind of 0 as placeholders on the right side again. And now I'm collecting quadratic, linear, and constant terms on the left side and color coding them. I think I didn't correctly color. I don't know how the colors got off of line, but you got me here. Negative 4a needs to be 4. Negative 6a minus 4b, that needs to be 0. And the third collection of things, 2a minus 3b minus 4c, needs to be 0 also. I apologize, the color coding didn't work out there. Okay, so setting those all up as a system of 3 equations and 3 unknowns. Oh my goodness, these are going to just be brutal. Oh, well, maybe not. Sometimes they may be, but this isn't too bad. I mean, we just get A right away. It's almost not a system of 3 equations and 3 unknowns. It's so simple. We get A right away. That actually gives us B then, almost immediately as well. And again, I don't want to rush ahead. Did you do this on your own? Did you hit pause? Did you get for A, B, and C these things? Good. So then, again, hit pause. Can you write down the entire solution to this differential equation, the general solution? It's going to be YH plus YP. So this time YP is this polynomial expression, this quadratic with the coefficients that we've just found. Okay, to round this out, let's show you one that looks really pretty terrible. All right, so imagine now you have on the right side some combination of these functions. Boy, how many constants is that going to be? Well, you're going to have a giant UC set here. It's going to be from the x squared term, from the exponential term, and from the sine term. You're going to get all these functions and all of their derivatives that are possible. How many constants is that going to be? Well, it'll end up being, what is that, 6 constants? Yeah. Now, fortunately, we have already solved each of these. This actually kind of amounts to, here, I should make that animation go away there, but this actually amounts to just solving separate systems that we had on the previous slides, right? So you're going to get this. You might think, oh, well, this is going to result in a system of 6 equations and 6 unknowns when we collect constants, and you would be right, but it's the system is able to be kind of separated into parts. There's a system of, it's really kind of a system of 3 of the equations that will involve only A, B, and C, 1 equation that will involve just D, and then 2 equations that will involve E and F. And of course, those all have the same system. This is the same set of problems we did earlier. So you'll notice this is kind of a fun last little summary of how we could handle all the previous things we did here, and the combined solution is there. So kind of a fun last example there. So we're going to take this deeper in the next one. I've got you might think, oh, I love this method. It's easy. I'm afraid there are some issues though that are going to come up. So we'll let you think, at least for now, that this is easy, but there are some snags that we're really going to have to think hard about. So we're not done with section 3.6. Stay tuned for more.